Okay, well, it's a couple minutes after, so I'll get started. And we're going to talk about structural equation modeling today. And so in terms of an outline here, I'm going to do a little bit of review of correlation and regression. Then we'll talk about path analysis and what a latent variable is. And then talk about, well, factor analysis. Probably most everybody is familiar with exploratory factor analysis. And we're going to focus on what's called confirmatory factor analysis. And then I'm going to go over three specific examples here. A factor analysis related to financial security, and then we'll look at a couple of structural equation models of teacher wellness and then heart failure. And then I'll say a little bit about generalized structural equation modeling. And then I'm going to end up with talking about some software for doing structural equation modeling. So as you recall or may or may not recall, in linear regression, we have a dependent variable or the outcome variable that's continuous and assumed to be normally distributed, although it doesn't have to be exactly normally distributed. And so we have the regression equation where we have the regression coefficients, the betas, and then the x's that are the independent variables. And so the interpretation is that a regression coefficients are the change in y for every unit change in x. And if you have a multiple linear regression, then it's adjusted for all other dependent or independent variables in the model. And so we're going to add to this by talking about a structural model. So in regression, most variables are assumed to be measured without error. And for some, like survival or age, we can pretty much assume that they're measured without error. Other outcomes like stroke or MI are usually adjudicated by a panel of experts or a group of experts. So those may not be exactly measured without error, but they're usually regarded as such. However, many things that will even outcomes or variables that we'll look at in structural equation modeling are measured with error. And this is particularly true of patient-reported outcomes like the SF-36, or now I guess it's the SF-12, the Seattle Angina Questionnaire, Kansas City Cardiomyopathy Questionnaire. Those all contain what we call measurement error. And so the thing about structural equation modeling is we're going to be able to estimate what the measurement error is for different outcomes. So the first thing I want to talk about is path analysis, which is basically just doing regression in SEM framework. And so we're going to have a structural model, but the thing about path analysis is that all of the variables, both the outcome variable and the covariates, are all observed. That is, there are variables that you have some actual measurement on. And the thing in path analysis that we'll be able to do is to estimate the correlation between the covariates. And so we're going to be able to identify covariates that are moderators versus covariates that are mediators of the outcome. And we'll give example of those and what is meant by that. So let's say that we have some outcome we'll call it administrative performance score, and that we have three variables that we want to look at that might predict that score: age, sex, and income. And so what we are going to do then is we're going to indicate in our path analysis the relationship here where age and sex and income all supposedly predict the performance score. Now, in this case, it might be that we have a relationship between age and income, and maybe between sex and income. And so our model here is going to be that age and sex are moderators of income. That is, that they interact with income to predict performance score. So this is the basically the idea of an interaction in analysis of variance or in regression, where the outcome is not the same at all levels of the covariates in this case. So there might be a difference in score related to income between males and females, and then also a difference related to age. And so what we're going to do then in our analysis is we're going to estimate the regression coefficients, the betas, for each of our predictor variables, our independent variables. And then we also will estimate the correlation between age and income and sex and income. And so when we have a diagram like this, where we have the bidirectional arrows, we're indicating a correlation, and that we are saying that there now is an interaction, or that age and sex are moderating variables in predicting outcome. So here's an example where we're looking at an outcome of teacher burnout. And this is measured with an instrument called the ProQual. And so what we're saying here is that variables of job demands, age, and then teacher support are our predictor variables, our independent variables. And so we see that what we're saying here is that job demands, age, and support just by themselves don't really identify the best prediction model, that we also have demands by support interaction, the age by support, and then we have a demands by age interaction. So we're saying that there's an interaction related to each of the variables with each of the others. And so we see here that in our model that we have a relationship here between job demands and burnout of 0.52, which means that there's a fairly strong relationship between the two, but it's moderated by the interaction with age and with support. And so this is what our model is going to look like, and we're going to then calculate some statistics that tell us how well our model fits. Now, on the other hand, so we have the same three predictor variables and the same outcome, but this time what we're going to say is that age is a mediator of performance score. And so our diagram is going to look like this, where sex and income are related, that is, they're correlated and they have an effect on the performance score. But in this case, age is a mediator. That is, age is not directly predictive of performance score, but it is of income. And so that's going to modify the regression coefficient that we get when we do our estimation here. And so we have the regression coefficient of age and income, and then sex and the performance score, and then income and the performance score, but income is mediated by by age. So in doing structural equation modeling, I've used just path analysis here. We can distinguish between moderating variables and mediating variables. And so the basic difference is that when you talk about moderation, we're essentially talking about an interaction. And a mediating variable is a variable that doesn't have a direct relationship with our outcome, but it does affect one of the other predictors of our outcome. And so we would have a correlation then between sex and income. But this would be an example then of a mediating variable. And so in structural equation modeling, what we do is we're going to combine structural modeling, which we just looked at with the path analysis, with measurement modeling. And so the structural part is just the regression modeling that we've looked at. The measurement model then is looking at what we call a latent variable that we create from observed variables. And so some examples that you probably are familiar with are the SF36 or SF12 that has a physical domain, an emotional domain, a couple of other domains, and then you can get a total score. And so each of these domains, physical domain, emotional domain, so on, is what we call a latent variable. That is, there are particular observed variables that go into comprising this latent variable. And another example is the cardiovascular questionnaires, the CL angina and the KCCQ, that have different domains, like for the SAC, physical limitation, angiostability, and so on. And for the KCCQ, we have symptom, physical function, a quality of life dimension, and a social limitation dimension. And so these are all latent variables. That is it's observed directly, but it's believed to be made up by other observed variables that we get some actual measurement on. So we'll give you some examples of this as we go along here. So we need to be familiar with SEM symbols. So when we do as looked at, whether we do a path diagram or look at a SEM model, a rectangle indicates observed variables. An oval latent variables, that is, our latent variable is an unobserved variable. The unidirectional arrow indicates regression coefficients, or when we look at latent variable factor loadings, that if you're familiar with factor analysis. And then a bidirectional arrow is going to indicate a covariance or a correlation between variables. And then, as I mentioned, we're going to be able to estimate error variance between variables, or the relationship between variables where their error variance is also correlated, and that's indicated by a circle with a unidirectional arrow. So as an example here, I'll show you how this looks in the SEM diagram for a latent variable that we are going to say is comprised of 5 different observed variables. And so if this is our model here that we're looking at, then this is what's called confirmatory factor analysis. And so we have the factor loadings of each observed variable on the latent variable. And this would be analogous to exploratory factor analysis, where you just allow the analysis to choose variables based on certain criteria usually related to the correlation between the variables. But in this case, when we do confirmatory factor analysis, we're specifying a model beforehand, and then we're going to see whether we have a good fit of the model or not. And so our evaluation is going to, first of all, look at the test that we call the likelihood ratio. And this is basically a chi-square. And you have a certain number of degrees of freedom. And so when we do the likelihood ratio test, in contrast to do hypothesis testing, where you're usually looking for a p-value that's significant, that it's less than some specified alpha error rate like 0.05, we're going to look for a non-significant p-value. And if we get a significant p-value with our likelihood ratio test, this means that our model doesn't fit. Another measure of fit that we're going to look at is the root mean square error approximation. And this, we want to be fairly small. Then the comparative fit index, which is a measure of the fit of the model. We want that to be fairly high. And then the standardized root mean square residual. We generally want that to be low, but that sort of depends on the model itself. And then finally, what we want to look at is a reliability index, which is giving us a, in measurement terms, a measure of reliability of our model. And this is going to be a number between 0 and 1, 1 being perfect reliability and 0 being no reliability. And so in addition to looking at the factor loadings, then we can also look at correlations between the variables themselves. And we can specify if any of these variables are correlated or whether they're all independent of one another. So in terms of the model evaluation, as I mentioned, the likelihood ratio test, we want a non-significant p-value. And ideally, if we get a perfect fitting model, the chi-square will be equal to the degrees of freedom. That's, hardly ever achieved, but that's what we're kind of looking for. And then for the root mean square error, the formula for that, but basically the smaller it is, the better the fit. And so here we want to look for something that's less than 0.05. And for the fit index, the larger the better. And so ideally we'd be looking for something around 0.9 or better. And then the residual error variance, say generally the smaller the better, but that will depend on the correlation between the variables. And then the reliability index, as I mentioned, we want something of 0.7 or greater. Usually it'd be really good if we had a 0.8. But that's in terms of the reliability index, we would look for something fairly high and close to 1. So here's a measurement model for financial health. And so we have 5 different variables that we've measured. That is whether our income is greater than our expenses, if we have a checking account, a savings account, if we're in debt, and then if we have a financial plan. And so the numbers there on the that are indicated, the 0.73, 0.65, these are the factor loadings. So we can see that the first 3 have pretty high factor loadings. The last 2 not so great. But our reliability index is only about 0.4, so we don't have a real great model here in terms of the reliability. So if we change this now, where we eliminate 2 of our variables and we look at just 3, income greater than expense, the checking and savings account, then we see that we get a model that has some better statistics. However, our chi-square variable is statistically significant. The degrees of freedom in the actual chi-square value are quite different. So we would have to conclude that even though our reliability is fairly high, our model is still suspect, that it's not real, it doesn't fit real great. So when we do SEM building, as I mentioned, we're going to propose a model. This is not exploratory factor analysis. We're going to actually propose what our model should look like. And so when we figure out the model, we have the structural model, the measurement model, and then we're going to estimate the parameters, the regression coefficients, the factor loadings. And then once we have that, we'll take a look at our model in terms of the goodness of fit statistics. And if our fit statistics aren't what they should be, then we're going to revise our model. And so our goal here is to get a model that best represents our data. And so it might take several revisions of our model to come up with the best fitting model. And so we're going to look at, and I'm mentioned here, in this case, the R-squared value is going to be, as in regular regression, an important statistic to look at. The variance in the data that is explained by the model. And we want this to be fairly high. So my first example, I'm going to look at teacher well-being. And so we have the variables burnout, anxiety, depression, which are measured by particular instruments, job demands, job support, job control, parental support, secondary stress, risk, resilience, and then some other demographics like age, race, income, experience. LEA is an indication of whether it's a public school or a private school. And so in terms of the variables here that the investigators were looking at, the teacher well-being, so that's our latent construct. And we're going to use the variables of depression, anxiety, and burnout to define that latent construct. And then we're going to look at these other variables over here as predicting that latent variable. And so they kind of diagrammed here what they thought would be the relationship. So what we want to do is put these in an SEM model, estimate the parameters, and then see how well our model fits. So here's our first model, or one model anyway. And so our latent variable here, we've called mental health. At the end, we'll see they ended up calling that something different. So the variables that define our latent variable are burnout, depression, and anxiety. These are all measured variables. And so we have the factor loadings, 0.81, 0.7, and 0.7, which are pretty good. And then we have our job demand, secondary stress, and parental support. And then you can see the different relationships. I'm not going to take time to go through all of the relationships here, but you can see that the covariates of race, income, and school type have hardly any relationship at all, any impact on mental health. Experience some, but not much. But if we look at our fit statistics, we see that it's nowhere near a good fitting model. Our chi-square is statistically significant. The mean square errors are quite high. The fit index is only 0.63 and our R squared is only 0.5. So now we need to do some adjustment to our model. And so what we're going to do is take away some of the variables, like because some of the covariates didn't appear to really impact mental health. We took those out. And so now we're just left with job demands and secondary stress. And then we're suggesting that parental support doesn't directly affect mental health, but it's a mediator because it has an effect on job demands. And so you can see that our regression coefficients here, 0.56 and 0.34, indicate that there is a pretty good relationship between job demands, secondary stress, and their influence on the latent variable mental health. However, again, our fit statistics show that we don't have a really great model. Chi-square is 15 with only 3 degrees of freedom. So that's, of course, statistically significant, and our R squared is actually less than 0.5. So it's back to the drawing board. And so here's another model where we put some of our covariates back in and looked at the relationship of these variables to mental health, which again, our mental health variable is defined by burnout, depression, and anxiety. And now we have a model that still isn't fitting very well, although our R squared is increased to 0.6. Our chi-square is still statistically significant. Again, even though we put these covariants of race and income back in, you can see that they still have little impact on mental health. And so here's another model where we've adjusted some of the variables that directly influence mental health, demands, secondary stress, and risk. And then we're suggesting that there's a interaction between demands and risk, secondary stress and demands, and secondary stress and risk. So here we're proposing that there are these variables are moderating variables. So again, we're doing our fit statistics are still doing not real great because we still have a significant chi-square, but our R squared is improved and the fit index is improved. And so we go to another model where now we take out one of the predictor variables, and instead of having it be a predictor variable, we're now saying that it's a variable that would relate to mental health. And so we put secondary stress over on this side of the equation. And what we've said is that there's an interaction between demands and resilience on impacting mental health. And so you can see the coefficients here. Resilience, we would expect, would have a positive impact, so we get a negative coefficient, whereas demands is again a fairly strong predictor of mental health. And so now our fit statistics are improving. Our chi-square is still pretty significant, somewhat significant. but our fit index and our mean square error are being reduced quite a bit. And then we go on here, and this time I color-coded the predictors so we know what's a predictor, what are moderators, and what are covariates. And in this model, we have, again, pretty good fit statistics, except that our goodness of our chi-square is still pretty close to being significant. So we think that maybe we can still improve on this model. And so in this case now, we've adjusted some of our relationships. As I say, I'm not going to take time to go through all of these, but looking at what are interactions between the variables. And again, we have put back in two of the covariates, race and the school setting, but again, they have virtually no impact on mental health. So now we get a chi-square that's not statistically significant, although the chi-square itself and the degrees of freedom are still fairly far apart, but our other fit statistics are looking pretty good. And then one more that we'll do here, where we'll basically take out the covariates of race and the school setting. And then now we get even better fit in terms of the chi-square goodness of fit, our mean square error, the fit index. The R squared is still almost 0.7. So you can see that by adjusting or rearranging variables in our model, that we can get at a model that fits pretty well. And this is the actual final model that we came up with, where we eliminated the other covariates, and we looked at just resilience, experience, economic hardship, and age, and their relationship with job demands. And now we're instead of calling we're renaming our latent variable emotional distress, which I realized probably better fits the variables that make up that latent variable. And so now our fit statistics are actually quite good. Our chi-square is almost 13 with 16 degrees of freedom, so that's getting pretty close. It's not significant. We have a small mean square error, and the R squared is 0.7, which is decent. So this was the final model that we actually ended up. So you can see that we go through a lot of iterations to come up with our best fitting model that describes our data. So this is stuff I don't kind of already said as we've gone along here, but what I want to emphasize that we can adjust our model in terms of the variables that we input or leave out. And even though in this case we were able to come up with a fairly decent model, you have to realize that when we change the relationships, then that will obviously change the fit statistics. And in our case, it turned out for the better, but that's not always going to be the case. It could turn out for the worse. So once you have your model built, then it's the last thing you want to do is look at the evaluation statistics. Okay, so I want to do one more, not in the kind of detail I did for the teacher well-being, but this is looking at stage D heart failure, and we want to look at primarily the quality of life and different variables that may affect that. And there's two different options: mechanical circulatory support and intravenous inotropic support, CIIS. And we're going to look at the latter model. And so then we have a number of variables that we want to look at and see if we can build a model for quality of life. So our quality of life data, we're going to use the Kansas City cardiomyopathy questionnaire. There's a time trade-off, the days at home, activities of daily living, and if the patient dies, the location of death at home or hospital. Then there are variables that measure treatment satisfaction, and then another set of measures that look at treatment burden. And so, for example, treatment burden is measured by the frequency of PICC line infections, ICD discharges, unplanned visits to the ED or to clinic, and then hospitalizations, both prior and after treatment. And then there's going to be laboratory data that includes hemoglobin, CRP, BNP, those sorts of things, physiological data like heart rate, blood pressure, and then medications that are typically prescribed for heart failure patients. So you can see that there's a lot of variables that the investigators wanted to look at in affecting quality of life. And then also they looked at nutrition and such things as pain, tiredness. So again, you can see there's a lot of variables that are going into this model. In fact, when we look at the model, we'll say, how can you possibly get a fit for that model? But anyway, this is what it looks like if we diagram this out. And so we have 6 different latent variables, the main one being quality of life, HRQOL. And so the variables that make up our quality of life latent variable mentioned are hospitalizations, the KCCQ, days at home, and so on. And then the treatment burden, satisfaction, we have 3 variables for that, medications, physiologic, heart rate, blood pressure, so on. Then we have the laboratory variables, hemoglobin, CRP, and so on. And then symptom experience, which are assessed by an instrument called the PROMIS, and it has different subscales on that. So you can see that the complexity of the model here, when you first look at this, you can say, oh, we're going to be able to do this. Is this model going to fit? And in fact, we had such a hard time fitting it that it didn't work out very well. But you can see by the bivariate and the single directional arrows, what we're proposing here. And so let me just point out a couple things. So like here, we're saying that the latent variables here some of them are correlated. All of them will have an impact on quality of life, but some of them, like medications and physiologic measures, this is only a one directional arrow that medications are going to influence or have an impact on psychologic function. This is not a correlation. In other words, this is not a bidirectional arrow here. And so you can see how we've diagram this to indicate the relationships between the different observed variables and the latent variables. And so, as I mentioned before, the betas are regression coefficients, the lambdas are factor loadings, the rows are correlations. And then I didn't put them here because it got too complex, is the relationship, the correlations between these different measures, which there no doubt would be, particularly like for the promise measures. Those are probably correlated, maybe not highly, but to some degree. So anyway, this is a really complex model. And to do this model, actually in any model, even if it's relatively simple, you're going to need a fair amount of patience to build this model. And I'm not sure there's a way of really determining sample size like you can for hypothesis testing, but for doing structural equation modeling, I would say you probably need a good 200, at least between 100 and 200 patients. If you're down under 100 patients, it's going to be very difficult to fit a model, even if it's not as complex as this. So let me make some, end up here by making some comments. The observed variables, like we've seen, if you're looking at surveys or patient-reported outcomes, try as hard as you can to use ones that have been established, that have established reliability and validity. If you just make up some questions yourself or scales yourself, then you're going to have to demonstrate reliability and validity of that measure before you can use it. And that's actually true if you're just doing straight up hypothesis testing. So it's always best to find measures that will be relevant to your study, but have been established as questionnaires that have been used in research. So we can do with structural equation modeling, we can compare parameter and model differences. And so in our last one, I said there were two types of heart failure models or treatments that we could look at, one being MCS and the other that we looked at the model CIS. So what we would do is we would form or develop a structural equation modeling for both. And then we could compare those by looking at the regression coefficients and the factor loadings and using the same variables that we did in the CIIS for MCIS and see if there's a difference between the two groups or whether it's essentially the same. Then as far as more complex measures, we can use generalized structural equation modeling where we can look at mixed effects models, that is repeated measures, or time to event analysis, survival analysis. And so those are extensions of structural equation modeling with more complex, and that those would be separate. I'm not going to go into those. Those would be actually separate presentations even in themselves. I've got a few references here that give some indication of basically how to do structural equation modeling, then some examples. And what I want to finish out with is talking about software for doing structural equation modeling. So there is free software out there for doing SEM. In R, there's a routine called LAVAN. I'm not sure, latent something probably stands for. There's a piece of software called Onyx. Then there's GSCA, and then Lizerl. Lizerl is a really old program. I'm not sure how much that's been updated, but that was a program I used back in graduate school to do structural equation modeling. And I'm not sure how these, how these work, and I'm not sure about the software that you have to pay for. I'm not sure about SAS. That probably has a module for doing SEM. I'm not sure what it is. I've never used it. The one I use is Instata, which is actually part of the Stata package that you buy. SPSS has a standalone package called Amos, and that at least in the past, you used to have to pay extra for, in addition to the base SPSS modules. So if you are so inclined to try SEM on your own, which is actually kind of fun to do, you can see if you can download some of the free software and see how it works. The thing about Stata, and I'm not sure this applies to the free software, it may, but we can build a model by either writing code, and you would have lines of code to do it, to specify your model and the relationships. And what I like about the Stata is that we can build a model by a graph, by using a graph or a diagram. We don't have to actually write the code. We can do it by graph, and Stata will write the code for us. So just as an example, so this is a Stata screen that has all the statistics you can use, and then SEM here. And so if I were to click on model building and estimation, this is what I would get. I'd get a blank screen that we can actually build the model graphically on. And so over here on the left panel, you can see the symbols that we have, the rectangles for observed variables, latent variables, or unidirectional and bidirectional relationships. And so T here stands for text, I believe. But anyway, so we can then build our model like this. So here I put in 3 observed variables, and then I added a latent variable, and then put in the regression coefficients here for, or the factor loadings for the variables with the latent variable. And then once I have the model, then I can go in and indicate which variables are the observed variables, which variable this is, this one, and then what I want to call the latent variable. And then up here, when I have all that specified, so it's just a matter of building your model and putting in the variable names in your data set, and then just click on estimation, and it will put all the estimation parameters in here. So I'll end there and see if we have a few minutes here. If you have any questions, I think, or if not, you can email me, or if you would like a copy of the slides and then the presentation itself. I believe Georgetown puts these out. The presentation, I think, on YouTube, which if you registered, you should have access to, or they should send you that information. So I think if anyone has any question, oh, I got one here, so let me. Okay, so the question is, what are the assumptions in an SEM model? So I'll just give a kind of a brief answer for that. As I mentioned right at the beginning, the assumptions for regression are that we have a continuous variable and that it is normally distributed. Now, as you probably know, in actually doing regular regression, the outcome doesn't have to be exactly normally distributed. In fact, you can violate that quite a bit. But obviously, the assumptions are that we have a regression type of model, and so the assumptions that apply to regression would hold here. And then, of course, when we're looking at the confirmatory factor analysis, that is building a latent variable, then obviously we're going to assume that there's going to be a correlation between the observed variable and the latent variable, and that is that it's going to that all the variables, the observed variables that we have, are going to correlate in a way that gives us good fit statistics. So that's so in looking at the assumptions, that's basically what you would look at in any evaluating a model, are those fit statistics that we looked at: the chi-square, the CFI, the root mean square error, and then the reliability index, and the R squared. All right, and any others? Okay, as I mentioned, I will put a copy of the slides out to the Georgetown folks, and they will send that along with the link to the YouTube presentation. So I want to thank you for your time, and we will, whoops, let's see, we had 2 questions here. Yes, you can use categorical variables in structural equation modeling for predictor variables. Typically, well, yeah, actually, you can also use those categorical variables in defining your latent variable as well. The latent variable won't be categorical, but the observed variables can be categorical. So if you just have a categorical outcome, then basically all you're going to do is logistic regression. Okay, I'll just wait another minute or two if there's any other questions. Okay, thank you for listening. And as I mentioned, we will see you in October. Thank you for your time, and appreciate your attention and participation.